Let's talk about using priority queues for sorting, and in particular a type of sort called a heap sort. So considering the following algorithm, we'll take n items and add them to a priority queue, and we'll do the type of priority queue that we've been looking at so far, where lower value corresponds to a higher priority, so things like the min heap. Then after we've added all of this data to the priority queue, we'll remove all of the data. We'll remove all n items from the priority queue. So we'll get items out in order from the highest priority, the lowest value, to the highest value, which is the lowest priority. So items will be removed in ascending order. We actually saw this example earlier when we inserted a bunch of information into a priority queue, into a heap to build the heap, and then removed all of the data from the heap. All of the items were removed in ascending order. So, sorted. So we've come up with a way of sorting. So let's look at how our three different implementations of priority queues compare with this approach to sorting. So first off was our unordered linked list approach, and if you remember, it was really good at inserting items. It could do that in constant time, but extracting the minimum required a lot of effort. We had to go through and we had to find the minimum value. So the sort process would require n inserts, so n times that constant time operation, and then we have to do n removes, so n times that extract min time, which is order n, so it's n squared. By the way, I want to again highlight that extracting the minimum value with our unordered linked list approach was the more complicated part of the process. We had to iterate through and find the minimum value. We've seen this pattern before. This is just doing selection sort. It's expending a lot of effort to select this minimum value. Okay, our second implementation was the ordered array, and keeping things in order required a lot of effort. So sometimes when we insert something, it requires n units of time. On the other hand, if we've ordered things in a well thought out way, removing the highest priority item, the lowest value, can be done in constant time. Okay, so again, we would have to insert n things, each one of which could be order n. And then after that, well, we've got to remove n things, each of which could be constant time. So this is also an n squared algorithm. By the way, the approach here is putting all of the effort on this insert process. This corresponds to another type of sort called insertion sort. Okay, our last approach here is using the heap, and we'll just go through adding our n things and then removing our n things. So this is an n log n sort, and that's quite a bit better than the n squared sorts that we've seen so far, and this is aptly named heap sort. There are other approaches to doing this. There are things called in-place heap sorts that use an array and perform the basic heap sort process all inside of a single array. Okay, so to summarize, we've talked a little bit about three different types of sorts that can be done with priority queues. So if we use our unordered linked list, we're essentially doing a selection sort where all of the effort of our sort is going into selecting the minimum item, and that's an n squared sort. If we use our ordered array-based approach for a priority queue, all of the effort is going into the insertion part of managing our priority queue, and this corresponds to a type of sort called an insertion sort, which is also an n squared sort, although there are some special cases where this can be much better. And then if we use a heap with our min heap priority queue, the effort to insert things and remove things is much more balanced, and we get an n log n sort. So this is considerably faster at sorting than our n squared sorts.